If you know much about biology, you've probably heard about the nucleotide bases that make up our DNA and our RNA. These bases are commonly represented with single letters, as our A, T, C, and G. And of course, these are very important because they make up our DNA, which then makes up our genetic code. Now, if we look at the chemical structure of these bases, we'll see a few key shared similarities between all of our four common bases in DNA. So they all have a cyclic structure, which also happens to be aromatic. And they all share the presence of nitrogen within that ring system. So these are the two common structures that are shared for all four of our bases. And then we'll have different chemical functional groups added on here to differentiate between our A, T, C, and G. The A and G both share this basic structure, and our T and C both share this basic structure. Now these nitrogens here are key for the overall function and behavior of our nucleotide bases. And in fact, these are our new functional group that we're going to be looking at today. So these are amines. The general structure of an amine is a nitrogen, which is then bonded to three different groups that could be either carbon chains or hydrogens. So it's similar to our amides, but without that carbonyl next to our nitrogen. These nitrogens, again, they provide a lot of the key physical properties of our bases, but the other thing is that they actually provide that name itself. Right? So if you've ever wondered about why these are called bases, right, we don't generally think of them as being basic compounds that we're using in acid-base reactions, but these amines that are present within our nucleotide bases actually do have some basicity associated with them. So it's the basicity of our amines that then gives our nucleotides their base name. As usual with our organic functional groups, we're going to be looking at the naming, the properties, and the reactivity of our amines so that we gain a better understanding of the purpose of that functional group within our organic molecules. Let's start by looking at the classification and naming of our amines. First off, similar to our amides, our amines can be classified based on the number of bonds they have to carbons. So if our amine has 3 bonds to different carbon groups, it would be a tertiary amine. If we have 2 bonds to carbon groups, and then 1 hydrogen, this would make a secondary amine. And then of course the primary would be if we have 1 bond to a carbon group and 2 other bonds to our hydrogens. Now our amines can also form a quaternary state as well. So if we use this lone pair and add on another carbon group there, we can make a nitrogen bonded to 4 different carbon groups. Now in this case, of course, since we've lost our lone pair, we're going to have a positive charge here. And so this will actually be a quaternary ammonium. So ammonium is referring to the fact that we now have a positive charge on our nitrogen, right? So that IUM ending is always indicating positive charge. And then this would be an ionic compound now. So it'd be a quaternary ammonium salt that would usually be bonding together with an anion in order to balance out our charge there. So our quaternary ammonium salts are a little bit different than our standard tertiary, secondary, and primary amines, just because they're now ionic and they're missing that lone pair. So we'll talk about them together with our amines, but they do have some key differences in their properties and reactivity that we'll be looking at later. Now that we've seen the different classifications of our amines, let's look at the IUPAC nomenclature of our amines. So the standard naming for our amines is as alkane amines. So we're going to be naming our parent chain, but then replacing the E at the end with our amine functional group. So our overall name being alkanamine. So in the case of our structure here, right, we have 2 carbons and then our nitrogen. So our carbon chain is 2 carbons long. That would make this a FN amine. Now it is also possible to name these as using our functional based naming system. So that would be as an alkyl amine, right, with our carbon named as a branch coming off of our amine functional group. Right? This is similar to the alkyl-alkyl ether naming system that we looked at when we were looking at our ether functional groups, obviously. Now we can use the same basic naming system for all our different classes of amines. Right? So if we add extra carbon groups on here, so let's say we have a secondary amine with a ethyl group and a propyl group. Right? These 2 carbons give us our ethyl group over here. These 3 carbons give us our propyl group over here. So this could be called a ethyl propyl amine using our functional based naming system. Or more commonly, we'll use the substitutive naming system, where we take this as our parent chain. So we have 3 carbons, that's propane, and amine, so that's propanamine. So we get our propanamine name. And then we're going to add our extra 2 carbons over here as a branch coming off of our amine. Again, similar to what we saw with our amides, we're going to put an N here instead of a number to indicate this carbon branch is connected to our nitrogen itself. So this would then be N-ethyl propanamine. We can of course extend this naming for our tertiary amines as well. Right, so if we have 2 different carbon branches coming off, and then our longer chain is our parent chain, this would be a NN diethyl propanamine. So we don't need anything special to indicate our different classes of amines. We would just have additional N groups here representing the different carbons attached to our amine group itself. Now, of course, in many cases we'll have other functional groups included with our amine function groups. In these cases, we need to know the priority for our naming system in order to understand which gets named as the parent chain and gets the first number in our priority, and which gets numbered as a branch coming off of that parent chain. So for our amines, in terms of priority, we have our amines at a lower priority compared to our alcohols and other oxygen-based functional groups. So alcohols will be at the top, above our amines, and amines will take precedence over our alkenes and other carbon-based functional groups. So for our molecule shown here, we're going to give the priority to our alcohol. So we're going to count from the right side to give our alcohol the lowest possible number. 1, 2, 3, 4, 5. So we have a 5 carbon chain. That gives us a pentanol. Right? We're using the OL ending here because our oxygen is taking priority for our alcohol functional group. And our nitrogen here of our amine is going to be named as an amino branch. So whenever we see amines, these are going to be named as amino substituents coming off of our alcohol parent chain when we have that higher priority functional group present. So we have our 4-amino, since that amine is at the 4th position. And then of course we still need to indicate where our alcohol is. So this would be 4-amino 2-pentanol. Now if our amine has additional carbon branches coming off of that, so let's say we have the same structure but with a methyl group attached to our amine. There are 2 different approaches we can use to this. So we can just indicate this as a N-methyl group. Again, indicating that's attached to our nitrogen and not to our main chain. So this would be N-methyl 4-amino 2-pentanol. Or we can also just include that methyl group with our amino to indicate that it's coming with our amino branch. So this would be a 4-methyl amino 2-pentanol. And these are both effective names for our amine here. Again, if we have other functional groups like alkenes, so let's say we have this amine here, so we have an alkene and our amine here, but our amine takes priority over that alkene. So we'd start with the carbon closest to our nitrogen. We number it to get our parent chain. So we have 8 carbons. So this is a octane amine. But we also have to indicate our double bond here. So we're going to have a oct, and then we have a 6 here indicating where our double bond is. En indicating that double bond. And then we can have our amine here. And of course, we might need a separate number here to indicate where our amine is at if it's not at that first position. Right? So in this case, I don't necessarily need that because if there's no number, we assume it's at the first position. But if my nitrogen was attached here, for example, instead, I would have a 2 in here. It would be oct6-ene2-amine. So we just add the extra En in there to indicate where our double bond is, but we're still giving the number preference to our amine since it gets the higher priority over our alkenes. Now let's take a look at the physical properties of our amines. So we'll start with our melting points and boiling points, which of course relate directly to the strength of the intermolecular forces between our amine molecules. Now our melting points and boiling points will vary between tertiary, secondary, and primary amines. Of course, this is similar to what we saw with our amides, right? Where as soon as we add in these hydrogens, we now have hydrogen bond donors that give us the possibility for hydrogen bonding between our amine molecules. Right? Our tertiary amine, it does have our hydrogen bond acceptor, but by itself, our tertiary amines can't hydrogen bond with each other. So again, primary amines will have the highest melting points and boiling points due to the stronger hydrogen bonding there, right, with 2 different hydrogen bond donors within our primary amines. Secondary amines will be in the middle. And our tertiary amines will have the lowest melting points and boiling points because they don't have any hydrogen bond capabilities when they're just by themselves. Right? So if you just have a mixture of tertiary amines, they're only going to be interacting through dipole-dipole interactions, which lead to those much lower melting points and boiling points. Now, of course, if we add in here our quaternary amines, so those can have ionic interactions, so they could have quite high boiling points or melting points. Again, as always, these will depend on our structure. right? These are larger structures always going to have a higher boiling point or melting point. So this trend is assuming that you have similarly sized molecules overall, just with differences in their classification. So again, we can add to this. Quaternary has high melting points, boiling points. Due to its ionic interactions. Now, if we compare our melting and boiling points of our amines with our similar alcohols, right? So alcohols would be most similar to our primary amines, where we have one bond from our alcohol to a carbon. Our alcohols, of course, have hydrogen bonding, but the difference between our alcohols and our amines is that our oxygen is much more electronegative, right? So with our more electronegative oxygen, that means that we're going to have a much more polarized bond between our oxygen and our carbon, and our oxygen and our hydrogen. And so our hydrogen bonding and our dipole-dipole interactions tend to be higher in our alcohols. So alcohols do tend to have higher melting points and boiling points than our amines. Of course, this will be influenced somewhat by the classification of our amine as well. Next, let's take a look at our solubility. Again, we see a very similar trend, right? As soon as we have hydrogen bond capability, we're going to become more soluble in water. So our primary amines will tend to be the most soluble, followed by our secondary, followed by our tertiary. Again, tertiary means even though they don't have hydrogen bond donor capability, they still can form hydrogen bonds with water through the hydrogen bond acceptor on our nitrogen there. But the overall solubility will be lower than our other amines that can also act as hydrogen bond donors. Of course, for all of these, right, that solubility is also going to vary based on the length of our carbon chain, right? For any molecule, if we increase the length of that hydrophobic water-fearing carbon chain, it's going to make that molecule be insoluble in water. So even if we have a soluble primary amine, we can still have an insoluble molecule if we have a very large carbon chain. The unique properties of our quaternary ammonium salts enable them to act as something we call phase transfer catalysts. So let's say, for example, we have an alkyl halide with a very long carbon chain, and we want to react it in a SN2 reaction. Now, our alkyl halide, if we want it to react in that SN2 reaction, we're going to be reacting with usually some kind of nucleophile, which is going to be anionic. Right? So let's say we're reacting it with our cyanide ion. So this is going to be negatively charged. Of course, most of our strong nucleophiles are negatively charged. And we usually have, of course, some cation to go along with this to balance out that charge overall. Now, if we look at our alkyl halide here, so this, of course, is going to be nonpolar. Right? We have a large carbon chain that's hydrophobic. We just have our one polar group over here. Overall, the molecule has relatively low polarity. Whereas our ionic compound here, right, is very polar. Right? And of course, that means that this is more going to want to dissolve in aqueous solutions, whereas this would want to be dissolved in more nonpolar solvents. So maybe things like hexane or something like that. So if we're trying to react these two together, they're not really going to want to mix in the same solvents, right? They each have different preferred solvents based on their overall solubility. This is where our quaternary ammonium salt can come in. All right, so let's take a quaternary ammonium salt. So we have our carbons attached to our nitrogen to give us that positive charge in our quaternary state. And our quaternary ammonium salt, right, so it's somewhat nonpolar, but then it also has that positive charge. And so our cyanide ion of our nucleophile can come in here and it can interact with our positive charge of our quaternary ammonium ion. So instead of interacting with just our small cation here that would be very soluble in water, we can interact with our ammonium ion that actually is somewhat soluble in our more nonpolar solvents, right? Because it does mostly have large carbon chains, it doesn't have an overall molecular dipole, right? It's just that positive charge that makes it more water soluble. So this can grab onto our nucleophile, pull it into that nonpolar solvent, at which point then we'd be able to complete our SN2 reaction and substitute that cyanide ion for our bromide. After the reaction is complete, our bromide ion would then be able to ionically interact with our quaternary ammonium cation again, and so that would prevent that bromide ion from being unstable in our nonpolar solution until, of course, our quaternary ammonium ion could release that into our water. So it's acting as a phase transfer catalyst here, right? Because it's basically pulling our cyanide ion from one phase, the aqueous phase, into the other phase, our nonpolar phase, so that we can react with our target reactant. So this is one of the neat applications of kind of the unique solubility of our quaternary ammonium salt. Now let's consider the overall reactivity of our amines. Now, of course, our reactivity is going to be heavily dependent on the electronegativity as well as the lone pairs and electron density near our amine. Now, our amine itself has moderate electronegativity, right? It's not as electronegative as our oxygen, since it's to the left of oxygen on the periodic table, but it is more electronegative than things like carbon or hydrogen, since it's to the right of those on the periodic table. So we will have electron density pulled from our carbons and hydrogens towards our nitrogen, so it'll be partially negatively charged, whereas our attached carbons and hydrogens will all be partially positively charged. Again, as we're pulling electron density towards our nitrogen, and of course our lone pair there also contributes electron density, that makes our nitrogen somewhat nucleophilic. So our amines do make decent nucleophiles. Now, of course, the other key reactive property of our amines is their basicity. This is something, of course, that I already mentioned in my introduction, right? So our amines are our most common biological bases. So this basicity is because, of course, with a moderate electronegativity, we do have a decent electron density here, as well as a lone pair that we can use for an acid-base reaction. But we're more willing to use that lone pair since we have a lower electronegativity than things like oxygen or fluorine. Right? So we're still willing to use that lone pair to react, but we do have those electrons available to actually react as that base. Now, both of these properties can, of course, be modified based on the structure of our amine. So if we add things like any kind of oxygens or double bonds, things that will use inductive effects to decrease our electron density, those will change our basicity. So if we compare our primary amine over there to a primary amide, for example, within our amide, you might remember that we have this electron donating effect where our nitrogen can donate its electrons up to our oxygen there to create a partial double bond between our nitrogen and our carbon. Now, of course, what this indicates is that we don't have as much of a share of that lone pair, right? Our electron density is lowered on our nitrogen, which then means that we have decreased basicity. Of course, our basicity is also decreased here because if we did react here, right, so if we react as a base, we'd then be producing our conjugate acid with our 3 hydrogens here and our positive charge, and now we don't have our resonance structure with our carbon and our oxygen here, right? So by reacting, we've eliminated that resonance and created something that's less stable. Again, that decreases the favorability of this acid-base reaction. So for any kind of amine compounds, whether we have an aniline, right, where we have an aromatic ring, or just a alkylamine with just different carbon groups, you always want to be considering kind of how will that acid-base reaction affect the overall stability of your molecule. Also, what other groups might be drawing electron density away from that nitrogen that would then decrease our basicity. So again, going to our aniline here, which is our amine group substituted onto our aromatic ring. Normally, our aniline can donate electron density into our ring system, right? So anilines are highly reactive towards electrophilic aromatic substitution because of this electron donation effect. If we react this as a base, we lose our lone pair and lose that electron donating effect. So again, our aniline will be a weaker base compared to just a plain alkylamine. So this is really just using our normal principles of acidity or basicity, right? Anything that stabilizes our initial reactant will reduce our reactivity or reduce our basicity, or anything that pulls electron density away will also reduce the electron density that we can use to react as a base and therefore reduce our basicity as well. Right? Those are our resonance and inductive effects that we looked at last semester when we talked about the strength of acids. Now, the nucleophilic nature of our amines allows us to do a variety of different nucleophile-based reactions. Of course, we've already seen this with things like the nucleophilic addition of amines to carbonyls, but we can also use this in more traditional nucleophile-based reactions, such as our substitution reactions. So if we take our simplest amine of ammonia, and we combine this with an alkyl halide. So here I have my bromopropane. So you might think this would be a great approach to make a amine. Right? So I can attack with my nucleophile, kick off my leaving group, and that would produce my primary amine. So initially I would get my positively charged amine here as I react with my alkyl halide, but then of course I can deprotonate this in order to get my amine. I'm just showing my bromine ion in this case, although usually we'll be doing this in perhaps aqueous solution, and then our water would be acting as the base here to deprotonate my amine. So, at this point I have a primary amine. However, the problem that I have here is that my primary amine is still a pretty good nucleophile. So if I have my primary amine, and of course I'm still going to have molecules of my bromopropane here in solution, I can actually react again. Right, so I can take that primary amine, attack my electrophilic carbon here, do my SN2 nucleophilic substitution, and now I've gone from my primary amine to my secondary amine. And again, after I deprotonate that, I end up with an amine that can react again in a nucleophilic substitution reaction. So this would continue on to a tertiary amine. And it could even continue on to a quaternary amine. So we refer to this as polyalkylation. So since in each step our amine regenerates its nucleophilic nature, and we can bond multiple carbon groups easily onto our nitrogen, we can just continue this alkylation process, and we'll end up with a mixture of products. Right? We'll get some of our primary product here, but then we'll get more of our secondary product, and more of our tertiary product, and some of our quaternary product as well. So it's not really a great approach if we want some specific amine product, right? Because we're always going to get a mixture. Again, when you have a mixture of molecules that are very similar, it becomes very difficult to separate them and actually get the molecule that you want. Now, one of the ways that we can try to solve this polyalkylation problem is by using an excess of our starting amine reagent. So if we use a lot of our initial ammonium in this case, then in that case, we're going to have a lot of this in our solution compared to a relatively small amount of our bromopropane. And so the most likely reaction initially, of course, is going to be that single alkylation reaction to our primary amine. Now, since we have a large amount of this, and we'll have a relatively small amount of our primary amine produced, since we are going to have a smaller amount of our bromopropane, it's more likely that our amine will continue to find bromopropane to react than that our bromopropane will find molecules of our primary amine. Right? So just by having an excess of our initial amine compared to our initial alkyl halide, we can tend to encourage a higher preference of our primary amine or secondary amine, since those will be not as likely to find our bromopropane and react. And that can kind of help solve our polyalkylation problem. It's still going to be not really a great approach to synthesizing amines. So in our next lecture, looking at the reactions of amines, we'll look at some of the other approaches that we can use to form amines, and then also some of the interesting reactions that we can do once we form our various amine compounds.